Wait, how is
It's
it
like 57.
how is it
No, that's fine. Then I have to look again.
That's why I was staying. Like a lot of
Also, my friend,
Did tech check you?
I mean, I got
Does every Indian where you be able to
it's like the garage. Very cool. That's how school will be there.
It's literally not that. I did, I gave it to them. I'm obviously the day I died. Factory is so fun.
It was still can't deal with the dog, so it doesn't.
Or meth.
No, I swear, I still look what kind of.
Factory is so like, factory and virgin, I was like, I never did it.
Yeah, it was fight.
Miss Mulligan, I'm back.
I'm afraid.
You remember Miss Mulligan?
But even very easier to.
Page 48.
I'll look on her.
I really think that guy. It's probably gonna be.
Okay, so this is a 2011 number 6. Typically, at least within the last, maybe 10, 15 years, number 6 has always been on the FR. There's 6 FRQs you're going to see on your BC exam, and number 6 is usually reserved for Taylor series or Lagrange bound or something involving with series. And if it's number 6, it's always going to be non-calculator. So you will get to use a calculator on all the practice tests and quizzes that we're going to take, but we kind of just have to kind of keep in mind, okay, that as we work this problem, that in preparation for the AP exam, this is meant to be non-calculator. All right, so it says let f of x equals sine of x squared plus cosine x. The graph of the 5th derivative of x is shown. So this is the 5th derivative of x. Write the first 4 non-zero terms of the Taylor series for sine of x about x equals 0. And then write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. So we're kind of building this from the beginning here. So we know what sine of x is. Let's go ahead and do that. We know sine of x is going to involve odd degrees, and the factorial are also odd. Let's build sine of x squared. So we can replace every x with x squared. Okay, everybody okay with adapting to the new exponent? So replacing the x squared in for the x, 2 times 3 is 6, 2 times 5 is 10, 2 times 7 is 14.
Is that plus dot required or?
No, it's just that if I want to say it's an equal sign, I need to put a plus dot dot dot. And if you want to do the first 4 terms, just put a squiggly equal sign.
Oh.
I don't know how much the graders are going to care about that, but just to let you know, like difference between equals and square and approximation, right? Because so technically we can say equal sign if we say dot dot dot, because if we keep going, then eventually it will equal to the exact value of sin of x. Okay, so we have part A done. Part B, write the first 4 non-zero terms of the Taylor series for cosine of x. Use the series in the series for sine of x squared found in part A to write the first 4 non-zero terms of the Taylor series for function f. So, they could have told us from the very beginning just to write the Taylor series for sine of x squared plus cosine x, but they're kind of building it up for us, right? They kind of say, okay, do one thing at a time. They're kind of helping the students kind of structure their information there. So that's nice to have this problem kind of broken up into 2 parts. Okay, so let's build cosine of x. We know that cosine has even degrees. So 2 and 2, 4, 4, 6, 6. And the 1 here is really x to the 0 power. So this technically is still part of an even degree term, x to the 0 power. So we want cosine of x plus sine squared x. So I'm going to take these 2 series and add them together. So there are some that overlap, some that don't. I'm going to just put them all in ascending order, and then if there's any overlap, then I can combine those like terms. Okay, this should be 4 terms here. 1 is by itself. We know the x squared, we're going to combine that. X to the 4th is by itself, and x to the 6th, we'll combine that. So when everything's said and done, we should be left with 4 non-zero terms. Okay, so I'm going to work to clean some of these terms up. So this is 1x squared minus 1/2 x squared. So that will give me positive 1/2 x squared. So I'm just trying to work on trying to get these to be combined into one term. I need to find a common denominator of 720. Six times 120, 720 divided by 6 is 120. So this combines to be what? Yeah, okay, so I'm gonna have my first four terms here. 1 plus
I'll just see.
mhm.
Do they have a preference? Do they have a preference for like leaving factorials in the denominator?
No, I think either is fine.
Okay.
Mhm. Yeah, on my key, I showed even on the AP key, it may show 6 factorial. Yeah, that's fine. Either is fine. Okay, find the value of the sixth derivative evaluated at 0. Well, we know this is related to the sixth derivative here because we know that anything involving with the sixth derivative is going to be this, right? It's going to be the sixth derivative evaluated at 0 over 6 factorial times x minus c to the sixth power. Right? We know that based off of Taylor series that if we were to build each term, eventually we're going to get to this term, and that matches nicely with this. We know 720 is 6 factorial, so the sixth derivative evaluated at 0 must be just what?
1.
Yeah, or negative 121. Yeah, the negative will have to go along with that.
So for that problem, since we calculated it in the step before, we don't have to show any word.
No, it's showing the word. No. Okay, part D. Okay, let the fourth degree Taylor polynomial that's given represented by p sub 4 of x about x equals 0. So it's basically a Maclaurin polynomial. Using information from the graph of y equals the fifth derivative of x, show that p sub 4 of 1/4 minus f of 1/4 is less than 1 over 1,000. So basically this is going through Lagrange error theorem, right? Because we know that this means the approximation minus the actual value is going to have an error bound of less than 1 over 3,000. Okay, so let's set up using Lagrange error bound, and I'll write the full formula here, and we can adapt to what we were working on yesterday. Now you don't have to do it on the test or exam. I just for purposes of making sure we know where everything is coming from. Okay. Let's assign some values here. N equals what? N equals 4. C equals X equals. Okay, so set everything up here. R sub 4 of 1/4 is less than or equal to the maximum, sorry. Which derivative do we want to look at? Fifth derivative.
Must be less than, because the problem says less than.
Oh, sorry. What do you mean less than?
Like the inequalities.
This one right here?
Yeah.
Yeah, that's fine. I think
Doesn't matter.
yeah, it doesn't matter.
Okay.
Yeah. Lagrange error bound sometimes has that less than or equal to, so I think either is fine. X minus C, so 1/4 minus 0 Okay, are we okay so far with everything that we put in place? Okay, so we want to find a safe upper bound for this, and they want us to use the graph because the graph is showing the fifth derivative at z. So we want to find the maximum value between what? 0 and 1/4, okay. Now, how is this scaled here? By 1/4, right? So this is 1/4, this is 1/2, this is 3/4. So basically, we just have to look at between here and here. So what's a safe upper bound that we can say? 40, right? That's a safe upper bound. I mean, I guess we could get away with saying 39, but they want us to use that safe value of 40. So 40 is going to be the maximum value. And we only care about between 0 and 1/4 because those are our x and c value, right? And we have the graph in front of us, and the fifth derivative is the next unused term. So 40 is going to go in place of that piece right there. Now, if we calculate this out, this is guaranteed to be less than 1/3000 because this adds up to be, or cleans up to be 1/3072. So we're able to prove using Lagrange error bound that this is true. Now, I do have to admit, like having to work all this out by hand is, I mean, that's just time consuming. So, it's almost like, oh, if we trust this, then we just say that this is less than 1/3000 without having to work all the way through. Okay, I'm going to let you guys use your calculator, but I'm just saying on the AP exam, this is non-calculator. So if you wanted to make sure this was correct, you have to kind of, clean this up. I guess it's not too bad, but still, it's just additional, calculation.
That's it.
feels
Okay to leave it on simplified. Right?
Yeah, you can say that this is less than 1/3000 if you trust that value. Another messy thing is having to do common denominators here. So that's just something that not all problems are going to have that where it's kind of calculation heavy, but that's a possibility with non-calculated portion. Okay, any questions? Okay. All right, so that's good. We're able to kind of see an example of a Taylor series FRQ. Lagrange error bound is not going to show up on every FRQ, but this is how it has shown up on one particular AP exam.
It's like pretty common.
Lagrange, it's not going to show up on every AP exam. So yeah, I would say, I don't know the percentage, but it's not every year that it shows up. But it's good for us to know it in case it does. Or if it doesn't show up on the FRQ, it may show up in some form on multiple choice.
This question also be about like convergence tests and stuff, like the entire infinite series.
It could. But typically, if it is about convergence, it's usually says, find the interval of convergence and just test the endpoints. And usually the endpoints is like, nth term test or alternating series test, things like that. So usually something like the integral test or P series, those are typically, we typically see that more on multiple choice section. But, we have so many years of AP FRQs we're going to try to do a little each day. So I think you're going to see a wide range of it. And I think in 2 months' time, you're going to feel very comfortable with any FRQ that they throw at you from a Taylor's perspective, Taylor series perspective. Okay, let's go to our test review. And we're going to start working on worksheet 1. Right, if in a series, S is equal to -1 to n plus 1 over 1 over 2 nq minus 1 is approximated by this series. What is the least value of k for which the alternating series error bound guarantees that the partial sum is going to be off by no more than 1 over 10 to the third power? And if we look at this, we kind of have an idea that this is going to be a converging alternating series. It's kind of within that family of P series. So we know this is going to converge. We know that we can rely on the first unused term to help us find the error bound. Okay, so. Okay, so we know that the difference between the actual sum and the partial sum is going to be less than or equal to the first unused term. And we want to make sure that the unused term is going to represent an error bound that is less than 1 over 10 cubed or 1 over 1,000. So if we want to find information about the first unused term, we can just replace every n with n plus 1 or replace every n with k plus 1. Right, I don't know why. Yeah, just find the value of k. So just replacing k with k plus 1, replacing n with k. So I'm just going to ignore the alternative here. Just replace the n with k plus 1. I just want to make sure, how many terms will allow so that the k plus first term is going to be less than 1 over 1,000. If I cross multiply here, divide by 2. Take the cube root. Solve for k. So in order for the k plus first term to be less than 1,000, to be less than 1 over 1,000, then k has to be greater than 6.939. So the smallest k value is going to have to be what? If the alternating series, we know that this is a alternating series It's an alternating harmonic series, which we know converges. If this alternating converging series is approximated by the partial sum of 15 terms, what is the alternating series error bound? We just find the what?
A sub 16.
Yeah, 16th term. Or actually, we only care about the absolute value of a sub 16, right?
So for this test, I'll be allowed to use a calculator.
Yeah, you could use a calculator on this, on my test. Okay, try number 3. We have a 4th degree Taylor polynomial. What is the value of the 4th derivative of 0? So if I just know how my Taylor polynomial is built in terms of the format, is the nth derivative evaluate at c for n factorial c. So the 4th term, which is b, or the 4th degree term will be so if we match up the terms, we know that this is equivalent to 5x to the 4th. So I know that this piece is the same as this piece here. So if I want to find the 4th derivative at 0 over 5, I can just set these equal to each other and just solve for the numerator portion there.
Sure. Where do you get 5x to the 4th from?
From this term here. Because I know the 4th derivative evaluate 0 must be involving the 4th degree term of my Taylor polynomial. So I know that these are talking about the same thing.
Thank you.
Okay, number 4. Function f has derivative of all orders for a real number. With real numbers, f of 2 equals -2, f prime of 2 equals 4, f double prime of 2 equals 8, f triple prime of 2 equals 14. Using the 3rd degree Taylor polynomial about x equals 2, what is the approximation of f of 2.2? So we're going to build out our Taylor polynomial. All the values are given to us. We just have to be able to put it into the proper form. So we know that p sub 3 of x. We know the first 2 terms is just going to be the y-intercept and then the slope times x minus c. So -2 plus the slope is x minus 2. And then from here, we can build the form with the factorial and the fractions. Okay. you can skip this step if you want. I just want to show you that ultimately we're using this form to help us find all the other terms. Okay, replace f double prime of 2 with 8, replace f triple prime of 2 with 14. And then once we have our polynomial written, we can replace every x with 2.2 and find the approximation by plugging into our calculator, replacing x with 2.2. Okay, any questions with first page? Okay, page 2, Lagrange error bound. See if you can set that up. Number 5.
It's scientific. Accepted, right?
Yes.
Does the fourth subscript on the P mean that it's like the fourth degree or that's the fourth term?
This right here?
No, on like right at the end.
Right here?
Yeah,
That's the 4th degree.
okay.
4th degree Taylor polynomial. Yeah, they don't have to mention Lagrange error bound for us to use it, as long as we know, oh, it's a Taylor polynomial, and they're asking us for the error of that Taylor polynomial, then that's indication that we want to use the Lagrange error bound.
Where's the 5, 6?
Good, the 5, 6. So we know that the nth derivative is going to be less than n over n plus 1. So this is our maximum bound that we can use. So if I want to find the fifth derivative, or the maximum value of fifth derivative, we just have to plug n in for n here. And because I want to do the first unused term, I want to use 5. So it'll be 5 over 6. And number 6 is also Lagrange error bound. Try that one. Let's keep working for a few more minutes.
Stream. Why is it centered about 0?
Which one?
6, sorry.
Because we don't see an x, I mean, there's x minus c here, but they're all hidden.
Okay.
If it wasn't centered at 0, it'll be x minus 2 cubed or x minus 4 cubed. X by itself kind of gives it away. Thank you. Okay, so worksheet 1 is 3 pages. So over the weekend, I want you guys to finish worksheet 1, as well as finish the rest of the unit packets. So the AP practice at the end of the packet, page 54 to 60. I'll send out a reminder on Sunday. Okay, all right, any response? Right.